One of the biggest problems in thermal process simulation and control is the estimation of heat flux, the rate at which heat energy is transferred from one system to the other, from one component to the other. There is hardly any manufacturing method where heat transfer does not play a crucial role. Take metal casting. An estimate of heat flux is essential for ensuring directional solidification. Selection of mold coats, chills in metal casting, etc. are governed by the heat transferred from the liquid metal to the mold. In heat treatment, the selection of proper quench media affects the final properties of the components. It is an essential input for process simulation, design of thermal systems, elimination of defects in manufacturing, etc. How do we quantify or measure it? Though we have sensors for measuring heat flux, say in a furnace atmosphere by flux meters, we cannot measure the heat flux when the process is inaccessible, like between the mold and the casting at the mold metal interface, or when it is too complex for calculations like during quenching. Spray heat transfer, heat due to a plasma or a welding arc are some other examples where heat flux cannot be directly measured. We can only estimate it by mathematical means. InverseSOLVER is the tool which can estimate the heat flux in all such cases. Let us see how InverseSOLVER works. We take here an example where a heated steel rod is quenched from one end by a jet of water. It is required to estimate the heat flux. The physics of water spray makes it very complicated for calculation by CFD approach. What we can do, however, is to measure the rate of cooling of the rod by a thermocouple located a few millimeters below the surface. By doing so, we will be measuring the effect of water jet. The process of calculating the cause from the effect is known as inverse solution. And the temperature is recorded till the end. The measured temperature is the only input to InverseSOLVER apart from the known material properties, thermal conductivity, specific heat, and density of the rod material. In the next step, we assume a heat flux and solve for the temperature at the thermocouple location, which is known as direct solution. This is done by finite element method. The error in the computed and measured temperature is calculated, and in the next step, a correction is applied to the assumed heat flux based on the error, and the steps are repeated till the error in the computed and the measured temperature is within an acceptable limit. Though the solution looks simple, mathematically it is not so, as the problem is classified as ill-posed, and therefore it requires special procedures called stabilization or regularization. InverseSOLVER addresses these issues related to conduction heat transfer with variable properties of materials, transformation of austenite during heat treatment with latent heat, conversion of TTT diagram into CCT diagram, hardness of quenched microstructures, and tempered hardness. It is thus especially applicable for estimation of heat transfer coefficient during quenching heat treatment. InverseSOLVER can be used in all cases where process is inaccessible for direct measurement, for the estimation of metal mold heat transfer for casting simulation, efficient design of water or spray cooling systems, selection of mold coat material and thickness in die casting for increased die life, measurement of contact conductance across metallic or non-metallic contacts, measurement of heat flux in all types of welding, friction welding, etc. for quality control, modeling heat transfer coefficient in boiling, condensation, radiation, forced convection, in space technology for design of heat shields and the like, in nuclear technology for design of complex cooling systems. InverseSOLVER, coupled with the newly designed tool reference quench probe, can be used for in situ determination of cooling characteristics of quenchants of all types.